Okay, well, thank you very much for the invitation. Well, it's great to see many familiar faces in the audience. I hope everybody is doing well, because it's been a long time. Yeah, well, it would be nicer to be in person, of course, and be more real, but hopefully sometime soon. Yeah, so today I will talk about a joint project with Mike Lipnowski, who is a number theorist down the road from where you are. And we'll talk, I want to tell you about closed geodesic and Frøyshov invariants of hyperbolic three manifolds. So yeah, let me just give a little bit of context and why, the kind of problems that we've been thinking about in the past few years. Yeah, so I guess just to put things in perspective, the modern theory of three manifolds uses, there's a lot of tools, but yeah, there's two set of tools which have been very successful among the others. So I guess, modern tools in three-dimensional topology. And I guess, yeah, so on one side we have Thurston's geometrization. And on the other side, we have Floer homology. Okay, so these are two kind of set of modern tools that have been very successful in addressing problems in three-dimensional topology. So let me say a couple of words about this. Yeah, so Thurston geometrization essentially says that you can use geometry, so Riemannian geometry, to study three-manifold topology. And in particular, what it says is, like, in some sense, the most interesting case of three manifolds is the hyperbolic three manifolds. Okay, so in some sense, a generic three manifold is hyperbolic, so it means a hyperbolic metric, a constant curvature -1 metric. And because of Mostov rigidity, this implies that geometric invariants, such as volume, injectivity radius, etc., are topological invariants. Okay, so this is very cool because now you can use geometry to study problems in topology. So for example, I think one of the easiest, if you have two three manifolds and you don't know if they're the same, the easiest way to tell them apart is like use some software in hyperbolic geometry like SnapPy and compute basic numbers in hyperbolic geometry like the volume, injectivity radius, that those are what we are very good at computing nowadays, and to tell manifolds topologically apart. Okay, so this is a very cool approach to topology in three dimensions. On the other side, we have Floer homology, and this is like somehow a very different approach to subject. So it's about studying certain nonlinear PDEs on manifolds and stuff to extract homological invariants. And the main there's various versions of this, and the one I'm the most interested in is the following. So today we'll be interested in monopole Floer homology. Okay, so this is obtained by studying the Seibert-Witten equations and was defined by equations on your three manifold, and it's due to Cronheimer and Rovka. So they constructed this package of invariants. And if you are more familiar with Hegel-Floer homology, you can also think about this. This is isomorphic to Hegel-Floer homology, which is you construct the same invariant, but instead of looking at Seibert-Witten equation, you count holomorphic curves in some space associated to your manifold. Okay, yeah, so I won't say the whole, even give it. It's a very rich package of invariants, but I would be interested in specifically in two very concrete things that this theory of monopole Floer homology gives you, and these are all topological invariants. So in particular, when b1 of y is 0, then you get two things. One thing is something called HM of y, and this is a finitely generated abelian group. Okay, and for those familiar with Hegel-Floer homology, this is the same as the reduced Floer homology. Okay, this is the reduced Floer homology. And the other object that were interesting is a collection of numerical invariants. So these are H, Y, S, and S, where S is an element in your H2. So you can think of these as spin C structures. Okay, and it is a collection of rational numbers associated to your three-manifold. And if you're familiar with Hegel-Floer homology, these are up to renormalization. These are the same as the correction terms. Okay. Yeah. So I won't tell you even how these are defined, but you can think there's a whole theory of homological invariants, and from there you can extract a group and some numerical invariants. And all these objects, they're very useful. So for example, so these are very useful. Okay, so for example, in the very special case, to each rational homology sphere, you have associated this finitely generated abelian group. And a very special case is that in which if Y is a null space, if this Floer homology group vanishes. Okay, and this has very deep geometric consequences. Well, I guess among other things, there's there's deep relations with the theory of foliations, a left orderability of fundamental group. I guess Steve is in the audience, so I won't say more about it. But yeah, so it's a very interesting question to understand which spaces, which rational homology sphere have vanishing Floer homology. Okay. Yeah, and on the other hand, this collection of numerical invariants is very useful to study relations with four-dimensional topology. Okay, so a lot of problems in topology really, even problems which are purely three-dimensional, maybe regarding, for example, unknowing numbers and stuff, can be translated in four-dimensional topological problems, which can be solved by looking at these numbers, which are some certain properties in special situations. Okay, so in some sense, this is another. So just to give a brief recap of what I said, we have these two theories, and they're both very useful to study certain problems. One, classification problems about problem interaction with four dimensions, or like problems in knot theory. Yes, I think a very natural question that one might ask is whether, and this is the question we've been trying to address. So is there any relation between hyperbolic geometry and Floer theory? Okay, so this is a very vague question, and I think it's interesting because a lot of questions in low-dimensional topology really, you can, as I said, the hyperbolic case is a generic case, and so usually a lot of problems, you solve them in the case in which there's no hyperbolic geometry, and then you're left with it studying the case in the hyperbolic geometry is present, and that's usually the hardest. So yeah, so I think understanding the relationship between Floer homology and hyperbolic geometry is kind of a fundamental question to address problems in low-dimensional topology. Yeah, so to be a little more precise, for example, one kind of question, a special case of this is like if you know everything about the hyperbolic geometry Y. So for example, well, I guess you can start with the volume, the injectivity radius, but you can ask more. There's much more information, like the length of all the geodesics and stuff like that. Can you determine its Floer homology? Okay, so this is also interesting from a more computational aspect of the theory. A lot of problems in low-dimensional topology boil down to computing these invariants, and in many cases these invariants you can compute them by using topological methods. But yeah, it would be great. In some cases, we have descriptions of manifolds which are not very well related to the approach that worked in this case. For example, surgeries or branch covers. So yeah, it would be good to have another set of tools to be able to compute invariants in Floer homology. And because we're very good at computing things in hyperbolic geometry, then this would be a very very useful thing to understand. Okay, so any question so far?
Is this related to the non-characterization by HM vanishing for L spaces?
Yeah, in some sense. So I guess for example, yeah. So talking, I was mentioning this relation. Yeah, it's called the L space conjecture, right? So the L space conjecture is proved in the case of graph manifolds, which is the case in which in the JSJ decomposition there's no hyperbolic pieces, and the hardest case is like the hyperbolic case. So if you had some understanding of Floer homology for hyperbolic manifolds in terms of hyperbolic geometry, maybe there's some way to understand the L space conjecture in that sense. Yeah. I don't know if this answers your question.
For
was that a yes or a no? I don't know.
I was trying to say this very useful to know that vanishing HM gives you an L space.
Oh, that's a definition. That's the definition of L space. It's if you're
that's the characterization of L space. So
well, that's the definition of L space. So yeah.
So I mean, I'm just wondering if because you want to relate to Floer theory and HM is related.
Sorry?
So you're trying to generalize that characterization to.
There's no, this is a definition. So I'm not sure which characterization you're talking about.
Oh, I'm sorry, just forget the question.
Okay, yeah, sorry. Anyways, yeah. Any other question? Sorry, maybe it was confusing because I said this, but this is a definition, and that's the hard part is giving geometric characterization of this thing. But this L space, L space is the Floer homology, reduced Floer homology is zero. That's the definition of what an L space is. Yeah. Yeah. So I guess what I want to ask. So I guess very very vaguely, what our work says the following. So the answer to the second question is yes, in certain situations. Yeah. Okay. In the way that if you tell us everything about hyperbolic geometry or some manifolds, we can tell you stuff about the Floer homology of the manifold without knowing much more about the manifold. Okay, just the hyperbolic geometry, which way, and and it works in practice too. Okay, so we have concrete examples which are methods to compute Floer homology starting from the hyperbolic geometry works. Yeah. Yeah, so there's two pieces of things. So there's this reduced Floer homology group, and there's the Frøyshov invariants. And let me start from the first one, because the answer of that is used to study the second case. Yeah, so so in the case of HMY, this reduced Floer homology. Yeah, so on one side we have hyperbolic geometry. And on the other side, we have Floer theory. Okay, so we don't really know a direct way to go from one to the other, unfortunately. But yeah, the way we know how to the way we found to relate the two is through the spectral geometry of the Laplacian on coexact one forms. Okay, so yeah, so there's some relation here and there's some relation here, and using this as a stepping stone, we are able to go from one to the other. So let me just quickly say what I mean by the spectral geometry. So the one forms on your manifold. So here I'm always assuming that it's a Riemannian manifold, so there's a Hodge decomposition. So the omega 0, that's H1. That's star. So we have this orthogonal decomposition in exact harmonic. Okay, and in our case, this will be 0 because we're assuming B1 equals 0. And we have here coexact forms. Okay, and the Hodge Laplacian acts on one forms and preserves this decomposition. So if you make it act on coexact forms, then it has spectrum lambda 1 star, lambda 2 star, and so on. This is the spectrum. Okay, so the stepping stone that we'll use here is this quantity here. So this first eigenvalue of the Laplacian on coexact one form. So it's kind of a weird quantity, but yeah, it somehow has recently, people have been interested in this quantity quite a lot because it's related to some interesting conjectures in number theory of Bergeron and Venkatesh, and that's how Mike and I started talking about this thing, just because this quantity appears in both my work and in his work. Okay, so let me describe the relationship 1 first. So this A. So the relationship A, which is the relationship between Floer theory and spectral geometry, is the following. So if you have Y hyperbolic rational homology 3-sphere. So here I'm assuming that it has a hyperbolic metric fixed. So if this first eigenvalue is strictly bigger than 2, then Y is a null space. Okay, so it's reduced Floer homology matrices. So in some sense, you can use spectral geometry to detect that something is a null space. Okay, and in some sense, just to give an intuition what this means, having a big first eigenvalue is some kind of measure of your space being small. You can think of, if you have a very small drum, you have a very high pitch. But if you have a big drum, you have a very small pitch. So you can think of this in some sense as some kind of measure of smallness. And you can think of, L space in some sense as some measure of smallness for your manifold from the Floer theoretic point of view. And this is, the L space conjecture relates this to, for example, existence of thought foliation, and you can think of that also as some kind of measure of smallness. You can think of a manifold that emits some thought foliation as some kind of a big manifold. Okay, so I think the heuristic for this result is like somehow, some measure of smallness in spectral geometry corresponds to some measure of smallness in Floer homology. Okay, so I won't say more about this this result, but in some sense it's an extension of the classical result due to Witten in some sense that positive scalar curvature things in Seifert-Weber theory have trivial invariants. Okay, so this is to prove this you somehow extend the ideas using Weizenbach formulas and stuff. Yeah.
So what if you started with a hyperbolic knot and you were asking, does it have a surgery which gives an L space? Can you say something? I don't know. I mean, what does? Yeah, I'm just wondering. Does this say anything about L space knots?
Yeah, that's a good question. I thought about it a little bit, and it doesn't seem to. So this lambda 1 star, it's very hard for it to be big. So in particular, if you do a sequence of large surgery on a knot, then it goes to 0 very fast. Okay. So if you have an L space knot, you have to do very large surgery, and in general, those will have very small lambda 1 star. So in some sense, this result doesn't fit very well with that picture. Yeah. So.
Does that also hold? Does it also get very small if you like the L space interval has 2 ends, right? And you're saying if you go to one end, lambda 1 star gets very small. If you go to the other end, is that happening as well?
Yeah, in the other end, it's less clear what happens. Yeah, so yeah, I don't know what happens in the other end. Yeah, but I don't have. I guess one problem is that here you need a very specific number, while in general, these kind of results are more in like asymptotic nature. So it's a little hard to get precise computation when you work with these quantities. Yeah. Okay. Yeah. So, but yeah, I don't know. Yeah, I guess you mean the 2G minus 1 surgery. Yeah, that's a good question. I don't know actually. Yeah. So.
Okay. Thanks.
Yeah, so this is how you relate Floer theory and spectral geometry. And for the other relation, the other direction, we use a completely different tool, which is the Cerebral trace formula. So let me just write it out. So this is some tool that come from harmonic analysis and representation theory. So we'll use the Selberg trace formula. Selberg trace formula for coexact one forms. Okay, so in particular, what we do is like, this gives you a relation between hyperbolic geometry and spectral geometry. So let me just write out what it is. So, if you have a function which is C infinity with compact support and R and even, and pick its Fourier transform. Okay. Yeah, so we have the following identity. So maybe I'll write it. So minus 1/2 the Fourier transform at 0 plus 1/2 the sum of the Fourier transform at the square root of these coexact eigenvalues. Okay. This is equal to another sum. So we have the volume of our 3-manifold. So this is all for a hyperbolic 3-manifold. H of 0 minus H double prime of 0 plus the sum over all geodesics of L of gamma 0. And I'll explain better what these terms mean in a second. Holonomy of gamma divided by 1 minus e to the CL gamma. Okay, I thought that breaking the 2 will make it fit. H of L of gamma. Sorry, it's a little cramped. I guess I should have. Okay, so what is this? So okay, on one side we have the sum over all eigenvalues of some quantity, and on the other side we have a sum over the geodesic. So you know, if you have a gamma closed geodesic in a hyperbolic three-manifold, then there are two naturally associated numbers. So one, and they give you the complex length of gamma, and you know that's the real part is given by the length of the gamma. So you know it's a geodesic, so you know it has a length, and then you know there's the notion of holonomy. So what's the holonomy? Well, you know you can pick a normal orthonormal frame and parallel transport it along your geodesic. And once you go back, you know, parallel transport preserves the fact of being an orthonormal frame, and you go back and you get another orthonormal frame, but you might get back to a slightly different, you know, a rotated orthonormal frame. So the holonomy measures how much you rotate while you parallel transport around your geodesic. Okay, so, and you know, in general, you know, any geodesic is gamma 0 to the n for some, you know, if you have a geodesic, of course, closed geodesic, and you go around it many times, you still get a closed geodesic. So in general, you know, there's a notion of being a primitive geodesic or a prime geodesic. Okay, so here, this is the gamma 0 that appears here. So we sum over all geodesics, not necessarily prime, the length of gamma 0 times the cosine of the holonomy of gamma. And then we have this weird quantity in the bottom where we have e to the complex length. Okay, so you know this is a very complicated formula, and you know you have infinite sums on both sides. But what's the important thing is that you know is that the structure it's actually if you look at it without thinking too much of the terms, it's nice because you know on one side we have to compute the thing. You know if I give you a function, you want to compute this thing. On one side, everything only involves the spectral geometry of the manifold, so it only involves the eigenvalues of the manifold. And on the other side, you only, to compute the sum, you only need to know the hyperbolic geometry of the manifold. So for example, you only need the volume and all these complex lengths of the geodesics. So the geometric side. Okay. And so this is good because, you know, in general, it's very hard to understand stuff about the spectral side just because, you know, understanding the spectrum is like solving finding the eigenvalues of certain the Laplacian, right? So it's about solving PDEs. So this is the hard side. Okay, just because it involves solving PDE, you know, trying to find solutions of PDEs essentially. And it's the easier side because, as I was mentioning at the beginning, we have a lot of tools to compute as quantities in hyperbolic geometry. So for example, there's code that, for example, we can use SnapPy, and you know you can give them a three-manifold, and they compute everything you want about. You know, you can compute all the geometric quantities that appear on the right-hand side. Okay, so the point then is that you know just because for any function, we can compute anything we want on one side, that allows us to get information about the other side. Okay, yeah, so, you know, so I guess the idea is that you can compute the right-hand side using SnapPy and use this to get info about lambda 1 star. Okay, so I won't get into the details of this. So our technology here is inspired by work of Bucher and Stromberg's on the number theory. But yeah, just to give you an idea, you know, how this can work in practice, is that, you know, let's look at a Weeks manifold. So this is known to be the smallest hyperbolic manifold. And, you know, it's, you know, there's a nice surgery representation on the whited link. And in particular, you know, we know that the Weeks manifold is an L space. But yeah, you know, so I won't even explain what this picture means, but, you know, using computation from SnapPy, you can somehow guess what the eigenvalues are. And in particular, we show using this method that I just using the trace formula, that lambda 1 star is actually more or less bigger than 9. Okay, so this means it's an null space. Okay, so you can use and these methods. Of course, there's other methods to compute that the Weeks manifold is a null space. But yeah, this method only takes as input, the volume of the Weeks manifold and the length spectrum, the length of all the geodesic, which have length shorter than like 5 or something. Okay. Yeah. So this is a kind of direction that allows you to prove that certain manifolds are null spaces, and you can use it to prove many more examples of this.
So, to what extent do these results depend on the fact that you're using a hyperbolic metric?
Yeah. So A can be generalized. So instead of a 2, you will have some other quantity depending on the metric. So 2 comes from the fact that the Ricci curvature of the hyperbolic metric is -2. So yeah, so A it can be generalized to any metric. B is really something about hyperbolic manifolds. If I give you a random metric, there's no way that you can find a relationship between geodesics and infinity. This is really a result. This result is proven by studying the representation theory of PSL to C. So which is the isometry group of hyperbolic 3 space. Mm-hmm. And if you have another metric, there's no such relationship that allows you to study things. Yeah.
I mean, I guess I asked because amongst other things that if you have a taut foliation, mm-hmm. Then Candel says you can start, say, from a hyperbolic metric and then do something to it and end up with one which, when restricted to each sleeve, mm-hmm. Gives you a hyperbolic metric. And I just wondered, is there, could you show that something with a taut foliation is not an L space, from this point of view?
Yeah, I think that would be very interesting. I think that's also a question I kind of thought about, but I didn't really get anywhere. Yeah, that seems, because the metric, this metric that you get on the top, which is adapted to the taut foliation, will not be very well adapted to Seifert-Weber theory, unfortunately. So it's a little, there's a little bit of a, they're not that compatible, I think. But yeah, maybe there's some way. Yeah, that would be very cool if there was. Yeah.
Okay.
Yeah. Okay. So this is a way to tell that a space is a null space by looking at just taking as input hyperbolic geometry. So you don't even need to tell me what manifold it is. How you found it. You just need to tell me just the hyperbolic geometry, and this will tell me whether it's a null space or not. In general, it's not a sufficient condition. So it might still be a null space if our thing doesn't work. So the other direction, the other part, if you have a rational homology sphere, that it's interesting, as I was mentioning, is this Frøyshov invariant. So that's it's in the title of this talk. So in this case, in general, these numbers are pretty hard to compute in general. But yeah, we in the special situation, so our working assumption will always be that the spectral geometry is somehow controlled. Basic observation is the following: is that if lambda 1 star is bigger than 2, then this Frøyshov invariance, you can compute it also in terms of spectral geometry. So in general, if you remember, if you've seen the definition before, these are defined as certain gradings of certain elements in special elements in Floer homology. Under this situation, this Floer homology can be rephrased purely in some kind of spectral geometry invariant. So in particular, you can show that there are this Frøyshov invariants are given by this eta invariants. So, and let me just these quantities are spectral asymmetries. These are the Tia Patadi-Singer spectral symmetries. Okay, so this is the first one is this spectral symmetry of this thing called the odd signature operator, and the second one is the spectral symmetry of the Dirac operator. Okay, so let me focus on the second, because the first one is somehow easier to compute because it's very closely related to topology. So in particular for hyperbolic geometry, there are easier ways to compute it. So really, if you want to compute these things, this is the hard thing, the hard part to compute. Okay, so let me just briefly tell you what these are. So once you have a spin C structure on a rational homology sphere, you have the Dirac operator, which is the one associated to the flat connection on the terminal line bundle. So so this is the Dirac operator. So you don't really need to know much about the Dirac operator, except that it's a diagonalizable operator. And unlike the Laplacian that we mentioned before, whose spectrum was all positive, the Laplacian is a positive operator. The Dirac operator, the spectrum is infinite in both directions. So you have T0, T1, T2, and then you have T-1, T-2, and so on. Okay, so the Dirac operator, the spectrum is infinite in both directions, and the spectral asymmetry really just measure in some sense how many positive eigenvalues there are and how many negative eigenvalues there are. Of course, this doesn't make sense because they're infinite in both directions, so it's defined in some kind of regularized way. So in particular, what you do is like you define the a function which is sum over all the non-zero eigenvalues of sine of Ts, Tj, divided by Tj to the s. And this is a holomorphic function defined for real value of s large enough. And you can see that if you plug in s equals 0, you just get, you get a sum that doesn't make sense, but it's really the number of positive eigenvalues minus this number of negative eigenvalues. But yeah, what you do is like eta of Dirac, this is defined to be the value at 0 of an analytic continuation. Okay, it's a holomorphic function, and it's a non-trivial result that it admits a analytic continuation which has a finite value at 0, and that's a natural way to make sense of this infinite sum, infinite spectral symmetry. Okay, and in general, it's just a real number. Okay, how much time do I have left? Sorry, what time is it? Sorry, I'm gonna.
11:40.
Okay, cool.
So you have another 10-15 minutes.
Yeah. Okay. Cool. Yeah. So of course, we would like to compute this number. So let me say, eta signature, as I was saying, there's other ways to compute it. This eta Dirac is somehow more complicated, because it's less closely related to topology, and yeah. So the way we approach this thing is like, again, using the Selberg trace formula, you can write this is a very complicated the definition, right? So if you want to use the definition to compute, well, first of all, you need to compute all the eigenvalues, then you need to and then you need to compute the analytic continuation, and then you need to find the value at 0, right? So that's not a feasible thing to do. But yeah, so the way we approach it is to use, again, some kind of Selberg trace formula, this time for spinor. So Selberg trace formula. for spinors. Okay, so let's say your spin C structure, say the spin. For simplicity, okay, in general, the spin C structure might be, there's a generally spin structure and then spin structure which are not spin. But yeah, so we can write out a very long formula for it, which a priori might not seem that you make progress from this definition, but actually it's a computable thing. So yeah, so let me just try to write it out. Let me see. So sum of sine of Tj divided by integral of Tj. So this is sum of Tj different than 0, infinity. So here again, you pick a nice function g, a nice even function g, dt minus 2 sum over the geodesics of L of gamma 0 divided by L of gamma, sine of holonomy of gamma divided by 2. And then G of L of gamma. Okay, and then you just divide everything by integral from 0 to infinity of Tg hat of T dt. Okay, so this is again a very huge sum. Yeah, and in principle you get two. If you start from G compactly supported, this is still an infinite sum because it's the sum over the geodesic it will still be infinite. Nevertheless, the thing we do. Okay, somehow we see like we made the problem worse because before we only had geodesics. Eigenvalues, but now we only have geodesics. The point is that these are infinite sums, but we can't truncate them. And the point is that once you truncate them, you get very good approximations. Okay, so truncate the sums.
Sorry, is there meant to be an equality somewhere in there?
Oh yeah, so I guess the equality is here.
Oh, okay.
This is the eta Dirac. Yeah, so this is the whole eta Dirac. Yeah. Okay, so let's say, and instead of a positive, instead of a compactly supported function g, it makes sense for certain reasons to pick a Gaussian. So yeah, so let me show you some results of this truncation. So let's go back to the Weeks manifold. So the Weeks manifold, these Frøyshov invariants are not they've been computed using topological method a long time ago, and in particular, I think the first appearance is the paper of Manolescu and Owens, where they use the fact that it's the branch level cover of this knot, which I think is 9 something. But yeah, so let's say we want to compute this super huge sum, but of course it's an infinite sum and it involves very complicated quantities, so we cannot compute all of it, but we can somehow approximate it well. And if you approximate it well, with some kind of approximation, you get these results. Okay, you can see that the numbers you get, this has 25 spin C structures, and they come into because of the symmetry, there really are up to symmetries there are only 5. So 25 spin C structures. Okay, and you can see that this number is very close to -1/2. This is very close to 1/10, and so on. Okay, so we're almost there in our computation. Computing this eta invariant is we cannot compute it exactly, but you can compute a very close. And these numbers that we get are the ones that Manolescu and Owens found almost 20 years ago. Okay. Yeah. So yeah, what's the point then? Is that the reason why we passed this is that we can we truncate the sum, but in this case we can give very good estimates on how much the error is. So so the point to get approximate computation to actual computation. Okay, the point is that we know info about the fractional part of the h of ys. Okay, just from the topology of the manifold in this case. You know, and this is, for example, if you just know the linking form of the manifold, you can extract. So you know, maybe it's a little cheating from our original goal of just using hyperbolic geometry, but you know, let me use also a little bit of topology, so the linking form. So you know, just knowing the linking form, for example, you can tell a priori that all these Frøyshov invariants, you know, these are the approximate values, but the actual values will be numbers of the form n over 10, for example. Okay, so just the linking form will tell you that. Yeah, so then all you need to do is like show that your truncation doesn't introduce too much error. Okay, so we need to give like concrete explicit bounds on these errors. So for example, you know, if we know that the Frøyshov invariant is a number of the form n over 10, if we give an error of at most 1 over 20, then you know we know exactly what's the Frøyshov invariant would be. Okay, and that can be done. That's the, you know, that's all the way up to this was somehow kind of the easy part. The hard part is to bound the error. And to bound the error, we use ideas from analytic number theory. So to bound the error, use explicit versions. So you know, we truncate the error on both sides. So we somehow cut off infinitely many eigenvalues and infinitely many geodesics. So we need to know somehow how many geodesics and how many eigenvalues we're losing. So to bound the error in this truncation, so we, you know, let's say we sum all the geodesic up to 7, and you know, we need to know how much error we introduce there. So we use you know, explicit versions of, you know, the Weil law. So the Weil law tells you the asymptotic of the number of eigenvalues on one side, and there are techniques inspired from analytic number theory that tell you very precisely how many there are in an interval. Okay, and on the other side is the prime geodesic theorem. Okay, so the prime geodesic theorem tells you, you know, how many geodesic, you know, the asymptotic of the number of geodesic in terms of the length, up to a certain cutoff of length. In the same way, the prime number theorem tells you the number of prime numbers less than n. And you can, in our case, because everything is so explicit, you can find versions in which you have very good bounds on the error too. So you can use that bound to those bounds coming from these ideas in analytic number theory to get bounds on the error obtained by truncating this sum. So this infinite sum, again, we go to a finite sum. And then, you know, from here, using topology, you get the final computation, you know, using the fact that we know the fractional parts, then that gives you a proof of the computation of this Frøyshov invariants. And I think this is where I'll stop.
Okay, well, thank you. So are there any questions? So, okay, if no one else has any, I'll start. So I guess you were looking at, your methods only seem to work for manifolds where the first eigenvalue is bigger than 2.
Mm-hmm, yeah.
How common are those?
Yes, that's a very good question. So it's, you know, we don't know if they're infinitely many, for example. So, okay, you know, we have, you know, a number of examples, maybe 40 or something in that we found in nature, like in the census or the Seifert-Weber dodecahedral space is like the biggest one volume-wise that we know. But yeah, it's very hard. You know, it's a quantity that tends to be very small in general, and you know you know, I guess the question in number theory, you know, the conjecture of Bergeron and I mentioned earlier is really about showing that this number cannot be that small. So in general, it's very hard to find. You know, we don't even know if we should expect infinitely many examples with this, that satisfy this property. Yeah.
I think Michael has a question.
Yeah, I have a question following up from Duncan's question. So you said that you need the volume to be quite big to get this eigenvalue inequality that you need. Is that right?
No. So in general, yeah. Yeah, I guess it's hard when the volume is big. I guess that makes it hard. Yeah, it makes it harder. Yeah.
Okay.
Yeah. So we know that if you put an upper bound on the volume, there's only finitely many.
Okay.
But yeah, the question is like if you let the other examples with arbitrary large volume, that seems open and hard.
Because this is reminiscent, you know, this isn't my area, but there's a theorem of Cheeger that says if you have a restriction, a lower bound on the volume, bound on the sectional curvature, which we have here, and an upper bound on the diameter, there's only finitely many diffeomorphism classes.
Yeah.
I don't know if that kind of result is kind of linked to this rareness of examples.
Yeah. I guess the point is that once you have a volume bound, then if you have an infinite family, then they get a cusp, right? So and you can show directly that a cusp gives you very small λ1 star. So that's yeah. So a manifold with large λ1 star needs to have, you know, no long tubes and no big balls actually. So it's kind of an interesting question, like if that's enough or yeah.
Okay, well, if there are no other questions, then let's thank Francesco again.